I want to spend another couple of minutes on problem 7. I want to look at this problem using Desmos. Now, the alternating series test tells us that a series will converge if B sub n. So in this case, B sub n is going to be all of this stuff here. If B sub n shrinks to 0. So you could go through and write this out as using x instead of n, take its derivative and show that it's negative, all that stuff. But I don't want to do that. What I want to do is just look at it and see that this thing actually does shrink to 0. Let's use Desmos to do that. Now, interesting thing with Desmos is if I put this in, y equals -1 to the n, and then n, and then over n plus 1, n plus 2. If I put that in there and then I look at this, you can see, and I just scrolled and lost it, but for a moment there, it was showing some little dots there for the values of n, or the values of y for the various n's. But it disappeared. I've not had good luck with using Desmos to plot sequences. So I'm going to change this to x. And one thing you'll notice right away, when I change all these to x's, there's still nothing you can see there. It doesn't like doing it because of this -1 to the x. -1 to the x, it runs into problems anytime that x is a fraction with an even denominator. But if I take that off, it gives me the function here. Now, remember, b is the series we have where all we're looking at is the absolute value of these things. So b is what I've got graphed here. And I want to see, is it shrinking and is it shrinking to 0? Well, let's zoom in. What I'm doing here, I'm holding down Shift and then zooming, scrolling here. And this shows me if we start at 1, that's going to be here. We are going down, so we're shrinking over here. And it is shrinking to 0. So the further out we go, the closer that y-coordinate gets to 0. So this thing is shrinking to 0. So b sub n shrinks to 0. Therefore, the series converges. Let me be particular here. Therefore, the original series converges because its terms are shrinking to 0 in absolute value, and they are alternating between positive and negative. All right, let's look at 8. On 8, we've got square root of n squared minus 1 over n cubed, and so on. So I want to, let's see, first up, if you look at this, it's kind of like the top has a degree of, it's like n to the first, because you're taking the square root of n squared. Basically, this is the dominant term, and down here, this is the dominant term. So let's look at what to compare it to. We'll compare to up top, that dominant term gives us just an n, and on the bottom we've got n cubed. So this is the same thing as 1 over n squared, and sum of 1 over n squared, we know this converges. It converges because it's a p series and p is equal to 2, which is greater than 1. All right, so let's set up a comparison. We've got 1 over n squared. Actually, I don't want to use that. In the comparison, I want to use this. These two things are equal, but this is closer to this in terms of how it's written. So over here I've got n over n cubed. And over here I've got square root of n squared minus 1 over n cubed plus 2n squared plus 5. All right, so now we have to look at the numerator and denominator. This over here, this has a bigger numerator, which makes it smaller. Up top, we have a smaller denominator, which also makes it smaller. And what I'm going to do, I'm going to write a, it's kind of like the numerator is trying to make it smaller, and the denominator is trying to make it smaller. So we can establish this inequality here. So what we know is this over here converges. This is adding up smaller terms. Therefore, by the comparison test, this converges. All right. Well, what about this next one? We've got cosine of n over 2, and then n squared plus 4n. All right. Cosine of n over 2. The thing is, well, first up, if you try to use the test for divergence, it would fail. Because the top is always going to be something between 1 and -1. Bottom is going to grow without bound. So it would give you 0 for your limit. So test for divergence is no good. So let's compare to. Now on the top we've got a cosine. So I'm going to put a 1 here in place of the cosine, because cosine is always smaller than 1. And on bottom we've got an n squared. Now this, it's the same series we compared to before. This is going to converge, because it's a p series with p equal 2. Now if you look at this over here, cosine of n over 2, if you compare that with 1, it's smaller. So that's going to make this over here smaller. And if you compare n squared plus 4n with n squared, this is a bigger number, which makes the overall fraction here smaller. So therefore, this works. So this converges by comparison. All right, let's look at 10. 10, we've got n squared plus 1 over 5 to the n. Now this one, we've got a mix here. What I mean by a mix is we've got, this is a polynomial and this is an exponential. So whenever you've got a mix of things like this, you want to use the ratio test. If you tried any of the other tests, they'd fail. So let's use the ratio test. A sub n plus 1 is going to be n plus 1 squared over 5 to the n plus 1. So now I'm going to do my limit. I'm going to do my limit as n goes to infinity of a sub n plus 1 times the reciprocal of a sub n. So I get that on top and this on bottom. And let's see, I can go ahead and cancel this and this. And it's probably helpful to rewrite it, because on top I've got, well, on top I've got n squared plus 2n plus 1. And on bottom I've got 5n squared plus 5. Those are my dominant terms, so this is going to go to 1/5. That's less than 1. Therefore, by the by the ratio test, this is less than 1, so by the ratio test, this is going to converge.